All right, so we've spent some time looking at Bragg's law, which tells us about diffraction peaks and the angle at which they occur. But Bragg's law is necessary, but it's not sufficient to understanding if a diffraction peak is going to appear in a diffraction pattern. We also need to know about the diffraction intensity. And so that's what we're going to talk about in this module. So in X-ray diffraction by a crystal, it arises from X-ray scattering, which we've talked about, collective scattering, either in terms of constructive or destructive, but it's occurring by individual atoms in a crystal. So scattering by individual atoms. And so specifically, it's by the electrons. So it's not actually the nucleus, which is the largest part. It's actually by the electrons, and so that's an important thing that we need to know. So the peak intensity is affected by how X-rays are collectively scattered in a given direction. So we're looking at this scattering from individual atoms, but how it collectively occurs in a given direction. So the electrons scatters the incident beam in all directions in space. But we just want to look at the one direction. So we can quantify the scattering intensity as a function of the angle. And that's the angle between the incident beam So the incident beam and the scattering direction. And we're going to call that 2 theta. So the intensity as a function of 2 theta is going to be equal to I naught over R squared times capital K, and then plus this function of the angle. So in this equation, I naught is the incident intensity, incident beam intensity. R is the distance from the electron to the detector. And I'm going to shorten electron to this here. And then K, capital K here, is a constant dependent on the atom's properties. So basically, this is an atomic constant, K. And the last term here, this function of the angle, we call this the polarization factor. If I can spell it. Polarization factor. So this gives us the angular effect of intensity. Like I said, it's a function of the intensity. All right, so this equation shows us the intensity of the scattered beam interacting with a single atom. So obviously we care not just about one atom, but that collective scattering that we talked about. And the collective scattering isn't just a simple sum of all these intensities from all the electrons in the atom, as you might sort of expect by this. Because we're dealing with scattering or diffraction, we're dealing with constructive destructive interference. And so destructive interference between electrons due to their position around the nucleus can result in destructive interference, or constructive but destructive. So the total scattering intensity of an atom at a certain angle is less than the simple sum that we have of all of these terms. So let me switch to the slides to show you a little bit more visually what I mean. All right, so this figure kind of shows schematically what I'm referring to in terms of the total scattering intensity being less than the sum, because we're dealing with a similar phenomenon to destructive interference that we saw in Bragg's law. So imagine that we're looking at, different electrons in an atom, and we want to look at the intensity. Well, the beam being scattered by this atom here results in the scattered beam Z. The one scattered by a different atom over here on a different position relative to the nucleus scatters to Z prime. And so those cause a phase difference. And so the effect, the net effect there, is destructive interference. And so the intensity is going to be less than just taking the sums of all the intensities, because we have diffraction occurring amongst the individual X-ray beams interacting with different electrons at different positions. So this is just kind of illustrating that effect. And so what we need to do now is look at the total. What happens for a given atom, not just individual electrons, which is what the previous equation showed. So now we want to look at atomic scattering as opposed to electron scattering. So that we refer to as atomic scattering factor. And we call this, we define this with the script F. And this is a function of scattering direction, scattering direction, and X-ray wavelength. And so that equation looks like the amplitude of the wave scattered by one atom over the amplitude of the wave scattered by one electron. So it's kind of a comparison between the scattering of a wave of one electron to the whole electron. So the intensity of the scattered beam that we have can be represented by this F, or atomic scattering factor. So let me show you a figure in the slides that shows us the relationship between this and angle and wavelength. All right, so this plot shows us the atomic scattering factor for copper plotted on the y-axis versus this factor involving the angle theta and the wavelength lambda. So basically, so assuming that the angle lambda is constant for this experiment, then the only thing changing here would be with increasing values here, we would have increasing angle. So what we see is that starting off at 0, which is what we would call forward scattering, this is where we have no relative phase difference introduced. And so there's no destructive interference, it's just constructive. And so we have the maximum intensity possible of the scattered beam compared to the incident beam. But as the angle increases and we go towards here, you notice that the atomic scattering factor decreases. That means that we have more relative phase differences introduced. So destructive interference goes up, and therefore the atomic scattering factor goes down. So the more angle that we have, the more destructive interference caused by these phase differences. And so that's an important thing. And that's why you'll always see this atomic scattering factor is a strong function of the angle. And so when we look at our diffraction patterns, the atomic scattering factor isn't a constant. It's dependent on the angle. And that's something that we want to make sure that we know. And so these values are tabulated, and I've put the tables from the Colody text in our Canvas folders, and those atomic scattering factors, you'll notice, are a function of this term. And so that's something that you have to calculate before you can calculate the atomic scattering factor.